So now it's time to connect. You've come up with wavelengths. All right. We've got a supposed hydrogen gas in a tube that's being electrified. Okay. Well, how do we verify all this? And it's going to bring us to the third page in our reference table right here, the energy level diagrams. So if you focus on hydrogen, that's where we are, there are a number of things on here that it looks like a ladder. You got down there an n equals 1 on the lower left, then n equals 2, n equals 3, n equals 4, so on. But what's going on here? What does this ladder have to do with anything? Actually brings us back to chem. You did this in chem. Here is a hydrogen atom in the ground state. In the center, you see that red nucleus, and orbiting about, you have an electron. Of course, this is the classical model, the Bohr model of the atom. It doesn't really look like this, but this captures a lot of what happens, so it's okay as a visual for our purposes right now. Anyway, so why do we plug in that gas tube down, then we run in the demo and then electrify it? Well, that gives it energy. So here, we can actually add energy. For example, if we add 10.19 electron volts, that's that little yellow flame in this image down here, the electron and the atom absorb energy, and the electron bumps up to a higher orbital. Of course, it can then relax, and in the process of relaxing, it actually releases the energy. Energy comes in the form of light. So this actually absorbs little bits of light called photons. They're just absorbed. And then it releases a little bit of light, also called a photon. Now, the type of light that gets absorbed and released depends on the transition here. If you want to jump to a higher energy level, you got to absorb more energy. Like we'll do this 13 eV. That's the second to highest. Jumped right up there. Okay. And now if you notice allow relaxation, there's a number of things it can do falling down. It can fall from the 5 as the 5th level down to the 4th, or 5th level down to the 3rd. And these 5, 3, 1, 2, all that, these actually are, if we come back over here, these are the energy levels you see on the left there, n equals 1, n equals 2, n equals 3. Those are the principal energy levels you studied in chem. So in the periodic table, those were the rows. So row 1, row 2, row 3, those are your energy levels. And so here, this all connects right back. And so this ladder diagram is like going down the periodic table. Here we have it drawing up. But as you go up or down in your periodic table, you go to higher energy levels. So, like we said before, you start out, let's see if we can do a little markup on here. Let us? Yeah. Okay. So you start out here, maybe, down in the ground state. And so that's just a regular relaxed atom. That's your n equals 1. And then if you plug in your device, you have electrons that are down here hanging out. And there are many atoms in this gas. So that supposed gas that's sitting there in that tube, there are many, many hydrogen atoms there. You could think of these, each lane here as a separate atom. There are many, 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 approaching Avogadro's number, something like that, atoms in there. And so when you excite them, when you add energy to them by way of electricity, some of the atoms will jump from this n equals 1 to n equals 2. Some will jump into the 3. Some will jump into the 4. Some will jump once they're in the 2 up to 3. Some will jump all the way up to 5. Some, once they're in the 3, will go to 4, and then 4 to 6, from 2 to 6. It doesn't matter. Basically, you plug it in, and you get lots of energy added to these atoms, and they all go, like we were seeing here, they all start jumping up. There, boom, absorb, jump up, that sort of thing. Okay, that part is the plug-in. But once they're up, do they stay up? And the answer is no. They actually relax. So how does the relaxation process happen? Well, the electrons that are, we'll color them green this time, they're up here in these upper levels, here, 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 wherever they are. These are lots of different, each E represents a hydrogen atom in a different excited state. So those hydrogen atoms, it's unstable to be in those high energy states, so they start to relax. Some of them will fall from, let's say, 3 to 2, or from 2 to 1, or from 3 all the way to 1, or from 6 to 3, whatever it is, they all start falling down, down, down. And so here you notice we have a big mess. I'm going to clean this up just so we can bring it back to what we're talking about. We can focus on perhaps one of them. Let's put one here in the n equals 3, and it falls down to n equals 2. Well, conservation of energy, where does that energy go? Where does in the n equals 3, it has an energy level of negative 1.51, and 2 is negative 3.40. The unit is electron volts. So where does that energy go? It actually went to lower energy. It went from 1.51 to 3.40. It's negatives, but energy is relative anyway, so the negative part doesn't really matter. What matters is it's going to lower energy, and the energy is going somewhere. Well, that energy actually gets emitted from the atom in the form of light. We sometimes call these photons, little bits of light. So the energy that gets lost, going from 1.51 down to 3.40, both in the negative, comes out, we can put a capital E over here, comes out in the form of light. Oh, is this starting to connect to our experimental setup? You plug in the big collection of hydrogen atoms, dump energy into them by way of the wall outlet, by way of electricity. You get them up into the excited states, and then they start relaxing. And when they do, they spit out light. Oh, so we're seeing something that actually is talking about connecting back to the whole orbital levels, excited, relaxed atoms from chem. Cool. Well, the interesting thing here is when you drop from 3 to 2, a certain amount of energy is actually released. Well, how do you find it? You just do the difference between these two. Oh. So what is that difference? Well, that difference comes out to, what's that? 1.89. So this thing comes out 1.89. The unit is EV, electron volts. So there's actually 3 of these I want you to do in particular. I want you to do the energy difference from n equals 3 to n equals 2, from n equals 4 directly to n equals 2, and from n equals, these color coding does not actually mean anything, n equals 5 to n equals 2. I just want to see the different ones. So I want you to do those 3 energy levels, from 5 to 2, from 4 to 2, and from 3 to 2, and come up with their energies in electron volts. That's part 1. Now, what do you do with that? That's good. Let's go over here. Well, we have to do some calculating with that. So, what do we calculate with that? It's not hard to calculate with that. It's actually a pretty easy thing. Right here. So that photon, there's that photon, that little bit of light that we were talking about before. Let's have it come in over this way. We had it coming in at 1.89 EV. Okay. How do we ultimately connect that to what we determined earlier in the slideshow there? We determined wavelength. So basically, how do we connect to lambda? We want to connect to wavelength. Well, there's our equation. Isn't that nice? You can take the energy, and this is a multi-equation, so let's use the pieces we want. We're going to use this piece with this piece. Ah, so we can take this energy, plug it in over here. We need this H and this C, which are actually constants. That's nice. They're both on reference table page 1. This one you've used plenty of times, so you can just go look it up. Be careful with this one. The unit provided on the front of the reference table is actually in joule seconds. You would have to convert it. So I'm going to give it to you in the unit of electron volt seconds, which will allow it to cancel with the electron volts we're bringing in. So this is not on the reference table. You would have to do a conversion to get it, which you could do. But it's 4.14 times 10 to the minus 15 electron volt EV dot S, electron volt seconds. I know it's a weird unit, a weird number, but go with it for now. So We've got this over here. We've got the speed of light that you know already. Put it in meters per second, just the way it's written on your reference table. We know the E photon. And now you can find the wavelength. Oh, I just disappeared the wavelength. I don't want to do that. You can find the wavelength. That's the goal here. In fact, you had 3 energies coming in, 1, 2, and 3, that pertain to 5 to 2, 4 to 2, and 3 to 2, those energy levels. And so I actually want you to find 3 wavelengths. The wavelength from 5 to 2, the wavelength from 4 to 2, and the wavelength from 3 to 2, using this equation right here. Not a hard thing to do. Little sloppy numbers there, I know, or sloppy is the wrong word, but scientific notation and division and all the rest of that. So just be careful with it. Don't be sloppy with it. And that will allow you to figure out 3 wavelengths. Now, how do these compare to what you calculated before? Definite error involved, but you might be surprised how close they are. They should actually be pretty darn close. And so do this, and then in the final moment, we're going to put color to our black and white image of the lines and see how nicely it lines up.